A Bose-Einstein condensate is a state of matter of a dilute gas of bosons cooled to temperatures very close to absolute zero. Under such conditions, a large fraction of bosons occupy the lowest quantum state, at which point macroscopic quantum phenomena become apparent. This state was first predicted, generally, in 1924–25 by Satyendranath Bose and Albert Einstein. History. Satyendranath Bose first sent a paper to Einstein on the quantum statistics of light quanta, deriving Planck's quantum radiation law without any reference to classical physics, and Einstein was impressed, translated the paper himself from English to German and submitted it for Bose to the Zeitschrift für Physik, which published it. Einstein then extended Bose's ideas to matter in two other papers. The result of their efforts is the concept of a Bose gas, governed by Bose-Einstein statistics, which describes the statistical distribution of identical particles with integer spin, now called bosons. Bosons, which include the photon as well as atoms such as helium-4, are allowed to share a quantum state. Einstein proposed that cooling bosonic atoms to a very low temperature would cause them to fall into the lowest accessible quantum state, resulting in a new form of matter. In 1938, Fritz London proposed Beck as a mechanism for superfluidity in Fourier superconductivity. On June 5, 1995, the first gaseous condensate was produced by Eric Cornell and Carl Wieman at the University of Colorado at Boulder NIST JILA lab, in a gas of rubidium atoms cooled to 170 nanokelvin. Shortly thereafter, Wolfgang Kettler at MIT demonstrated important Beck properties. For their achievements, Cornell, Wieman, and Kettler received the 2001 Nobel Prize in Physics. Many isotopes were soon condensed, then molecules, quasi-particles, and photons in 2010. Critical temperature. This transition to Beck occurs below a critical temperature, which for a uniform three-dimensional gas consisting of non-interacting particles with no apparent internal degrees of freedom is given by, where interactions shift the value and the corrections can be calculated by mean field theory models. Einstein's non-interacting gas consider a collection of n non-interacting particles, which can each be in one of two quantum states, and, if the two states are equal in energy, each different configuration is equally likely. If we can tell which particle is which, there are different configurations, since each particle can be in or independently. In almost all of the configurations, about half the particles are in and the other half in. The balance is a statistical effect. The number of configurations is largest when the particles are divided equally. If the particles are indistinguishable, however, there are only n+1 different configurations. If there are k particles in state, there are n-k particles in state. Whether any particular particle is in state or in state cannot be determined, so each value of k determines a unique quantum state for the whole system. Suppose now that the energy of state is slightly greater than the energy of state by an amount E. At temperature T, a particle will have a lesser probability to be in state by. In the distinguishable case, the particle distribution will be biased slightly towards state. But in the indistinguishable case, since there is no statistical pressure toward equal numbers, the most likely outcome is that most of the particles will collapse into state. In the distinguishable case, for large n, the fraction in state can be computed. It is the same as flipping a coin with probability proportional to p equals exp to land tails. In the indistinguishable case, each value of k is a single state, which has its own separate Boltzmann probability, so the probability distribution is exponential. For large n, the normalization constant c is the expected total number of particles not in the lowest energy state, in the limit that is equal to. It does not grow when n is large, it just approaches a constant. This will be a negligible fraction of the total number of particles, so a collection of enough Bose particles in thermal equilibrium will mostly be in the ground state, with only a few in any excited state. no matter how small the energy difference. Consider now a gas of particles, which can be in different momentum states labeled. If the number of particles is less than the number of thermally accessible states, for high temperatures and low densities, the particles will all be in different states. In this limit, the gas is classical. As the density increases or the temperature decreases, the number of accessible states per particle becomes smaller, and at some point, more particles will be forced into a single state than the maximum allowed for that state by statistical weighting. From this point on, any extra particle added will go into the ground state. To calculate the transition temperature at any density, integrate overall momentum states, the expression for maximum number of excited particles, P. When the integral is evaluated with factors of Kb and restored by dimensional analysis, it gives the critical temperature formula of the preceding section. Therefore, this integral defines the critical temperature and particle number corresponding to the conditions of negligible chemical potential. In Bose-Einstein statistics distribution, mu is actually still non-zero for BEECs. However, mu is less than the ground state energy. Except when specifically talking about the ground state, mu can be approximated for most energy or momentum states as mu0. Bogoliubov theory for weakly interacting gas. Bogoliubov considered perturbations on the limit of dilute gas, finding a finite pressure at zero temperature and positive chemical potential. This leads to corrections for the ground state. The Bogoliubov state has pressure. The original interacting system can be converted to a system of non-interacting particles with their dispersion law. Gross-Pitayevskaya equation. In some simplest cases, the state of condensed particles can be described with a nonlinear Schrödinger equation, also known as Gross-Pitayevskaya or Ginzburg-Landau equation. The validity of this approach is actually limited to the case of ultra-cold temperatures, which fits well for the most alkali atoms experiments. This approach originates from the assumption that the state of the Beck can be described by the unique wave function of the condensate. For a system of this nature, is interpreted as the particle density. So the total number of atoms is provided. Essentially all atoms are in the condensate, and treating the bosons using mean field theory, the energy associated with the state is, where, in the case of zero external potential, the dispersion law of interacting Bose-Einstein condensed particles is given by so-called Bogoliubov spectrum. The Gross-Pitayevskaya equation provides a relatively good description of the behavior of atomic BEECs. However, GPE does not take into account the temperature dependence of dynamical variables, and is therefore valid only for. It is not applicable, for example, for the condensates of excitons, manyons and photons, where the critical temperature is up to room 1. Weaknesses of Gross-Pitayevskaya model. The Gross-Pitayevskaya model of Beck is a physical approximation valid for certain classes of BEECs. By construction, the GPE uses the following simplifications. It assumes that interactions between condensate particles are of the contact two-body type and also neglects anomalous contributions to self-energy. These assumptions are suitable mostly for the dilute three-dimensional condensates. If one relaxes any of these assumptions, the equation for the condensate wave function acquires the terms containing higher-order powers of the wave function. Moreover, for some physical systems the amount of such terms turns out to be infinite. Therefore, the equation becomes essentially non-polynomial. The examples where this could happen are the Bose-Fermi composite condensates, effectively lower-dimensional condensates, and dense condensates and superfluid clusters and droplets. However, it is clear that in a general case the behavior of Bose-Einstein condensate can be described by coupled evolution equations for condensate density, superfluid velocity and distribution function of elementary excitations. This problem was in 1977 by Pellet-Minsky al. In microscopical approach, the Pellet-Minsky equations are valid for any finite temperatures below the critical point. Years after, in 1985, Kirkpatrick and Dorfman obtained similar equations using another microscopical approach. The Pellet-Minsky equations also reproduce Kolapnikov hydrodynamical equations for superfluid as a limiting case. Superfluidity of Beckon-Landau criterion. The phenomena of superfluidity of a Bose gas and superconductivity of a strongly correlated Fermi gas are tightly connected to Bose-Einstein condensation, under corresponding conditions, below the temperature of phase transition. These phenomena were observed in helium-4 and different classes of superconductors. In this sense, the superconductivity is often called the superfluidity of Fermi gas. In the simplest form, the origin of superfluidity can be seen from the weakly interacting bosons model. Experimental observation. Superfluid He4 in 1938, Pyotr Karpatse, John Allen and Don Misena discovered that helium-4 became a new kind of fluid, now known as a superfluid, at temperatures less than 2.17 K. Superfluid helium has many unusual properties, including zero viscosity and the existence of quantized vortices. It was quickly believed that the superfluidity was due to partial Bose-Einstein condensation of the liquid. In fact, many properties of superfluid helium also appear in gaseous condensates created by Cornell, Wieman and Kettler. Superfluid helium-4 is a liquid rather than a gas, which means that the interactions between the atoms are relatively strong. The original theory of Bose-Einstein condensation must be heavily modified in order to describe it. Bose-Einstein condensation remains, however, fundamental to the superfluid properties of helium-4. Note that helium-3, a fermion, also enters a superfluid phase at low temperature, which can be explained by the formation of bosonic Cooper pairs of two atoms. Gaseous. The first pure Bose-Einstein condensate was created by Eric Cornell, Carl Wieman, and co-workers at JILA on 5 June 1995. They cooled a dilute vapor of approximately 2,000 rubidium-87 atoms to below 170 Nk using a combination of laser cooling and magnetic evaporative cooling. About 4 months later, an independent effort led by Wolfgang Kettler at MIT condensed sodium-23. Kettle's condensate had 100 times more atoms, allowing important results such as the observation of quantum mechanical interference between two different condensates. Cornell, Wieman and Kettler won the 2001 Nobel Prize in Physics for their achievements. A group led by Randall Hullett at Rice University announced a condensate of lithium atoms only 1 month following the JILA work. Lithium has attractive interactions, causing the condensate to be unstable and collapse for all but a few atoms. Hewlett's team subsequently showed the condensate could be stabilized by confinement quantum pressure for up to about 1,000 atoms. Various isotopes have since been condensed. Velocity distribution data graph in the image accompanying this article. The velocity distribution data indicates the formation of a Bose-Einstein condensate out of a gas of rubidium atoms. The false colors indicate the number of atoms at each velocity, with red being the fewest and white being the most. The areas appearing white and light blue are at the lowest velocities. The peak is not infinitely narrow because of the Heisenberg uncertainty principle. Spatially confined atoms have a minimum width velocity distribution. This width is given by the curvature of the magnetic potential in the given direction. More tightly confined directions have bigger widths in the ballistic velocity distribution. This anisotropy of the peak on the right is a purely quantum mechanical effect and does not exist in the thermal distribution on the left. This graph served as the cover design for the 1999 textbook Thermal Physics by Ralph Bielin. Quasi-particles. Bose-Einstein condensation also applies to quasi-particles in solids. Manyons, excitons, and polaritons have integer spin and form condensates. Muons, electron spin waves, can be controlled by a magnetic field. Densities from the limit of a dilute gas to a strongly interacting Bose liquid are possible. Magnetic ordering is the analog of superfluidity. In 1999, condensation was demonstrated in antiferromagnetic TLC-UCl3, at temperatures as large as 14 K. The high transition temperature is due to the muon's small mass and greater achievable density. In 2006, condensation in a ferromagnetic yttrium-ion garnet thin film was seen even at room temperature, with optical pumping. Excitons, electron-hole pairs, were predicted to condense at low temperature and high density by Bohr et al. In 1961. Bilayer system experiments first demonstrated condensation in 2003, by Hall voltage disappearance. Fast optical exciton creation was used to form condensates in subsolvent Cu2O in 2005 on. Polaritone condensation was detected in a 5K quantum well microcavity. Peculiar properties. Vortices. As in many other systems, vortices can exist in BECs. These can be created, for example, by stirring the condensate with lasers, or rotating the confining trap. The vortex created will be a quantum vortex. These phenomena are allowed for by the nonlinear term in the GPE. As the vortices must have quantized angular momentum, the wave function may have the form where n is in the cylindrical coordinate system, and is the angular number. This is particularly likely for an axially symmetric confining potential, which is commonly used. The notion is easily generalized. To determine, the energy of must be minimized, according to the constraint. This is usually done computationally. However, in a uniform medium, the analytic form, where, demonstrates the correct behavior, and is a good approximation. A singly charged vortex for multiply charged vortices. Through Feshbach resonance involving a sweep of the magnetic field causing spin-flip collisions, they lowered the characteristic discrete energies at which rubidium bonds, making their Rb85 atoms repulsive and creating a stable condensate. The reversible flip from attraction to repulsion stems from quantum interference among wave-like condensate atoms. When the JILA team raised the magnetic field strength further, the condensate suddenly reverted to attraction, imploded and shrank beyond detection, then exploded, expelling about 2/3 of its 10,000 atoms. About half of the atoms in the condensate seem to have disappeared from the experiment altogether, not seen in the cold remnant or expanding gas cloud. Carl Wieman explained that under current atomic theory this characteristic of Bose-Einstein condensate could not be explained because the energy state of an atom near absolute zero should not be enough to cause an implosion. However, subsequent mean field theories have been proposed to explain it. Most likely they formed molecules of two rubidium atoms. Energy gained by this bond imparts velocity sufficient to leave the trap without being detected.